Good morning. This session will be about self-inductance. So at the end of this session you will know what is self-inductance, how to calculate self-inductance. Now this is actually falls in the same topic as electromagnetic induction. We have seen that whenever a current in the coil changes, an EMF gets induced. So let me draw a coil. Now we will consider a coil. Here is my coil or a solenoid, whatever you call, and let us say there are n number of turns in this coil. A coil with n number of turns, and current is passed through this coil, so that this coil actually acts as an electromagnet. Let me say I am connecting a battery through a switch. Now once the switch is closed and current starts flowing, we know the coil will behave as a magnet. There will be a magnetic field. Let us draw the magnetic field. One end will act as north pole, another end will act as south pole. These things we have already learned. You can refer the previous chapter videos for those things, like how the coil behaves as a magnet and which end will behave as north pole, which end will behave as south pole, etc. Now a current is flowing and the coil behaves as a magnet. So there exists a magnetic field around this coil. Now what happens if we change the current, or if we slowly reduce the current, or if we increase the current, or we quickly switch on and off the battery? We know that when the current changes in the coil, the magnetic flux also changes, because the strength depends upon the current. B is mu naught Ni. So the magnetic field is proportional to current. When there is a change in current, the flux linking the coil also changes, and there gets an EMF induced according to Faraday's law. When we change the current when I changes, I means current, flux linking the coil also changes. Flux linking the coil changes, and an EMF is induced. So this is the basic principle or Faraday's law, and this type of induced EMF is known as self-induced EMF. Self means itself, self-induced EMF. How can we define a self-induced EMF? Self-induced EMF is the EMF induced in the coil due to change of its own current, or due to change of its own current, because when the current changes, the flux linking the coil also changes. So the phenomenon of induction of EMF in a coil due to change in current or magnetic flux linking the coil of itself is called as self-induction. The EMF, I'll repeat, the EMF induced in a coil due to change of its own current or own flux is called as self-induced EMF. Let me write that. Self-induced EMF. Due to change of its own current, or I can write own flux, its own flux linked with it is called self-induced EMF. The EMF induced in a coil due to change of its own current or own flux linked with it is called a self-induced EMF. Now next we will see now what is self-inductance. What is self-inductance? Now when the EMF gets induced, we know the flux which links the coil is directly proportional to the current I. Why? Because flux is proportional to I. As current increases, flux will also increase, or the strength of the field will increase. When I decreases, flux will also reduce. First, flux is proportional to I, or I can write it as phi is equal to L into I. And here L is known as self-inductance of the coil. L is a constant known as self-inductance of a coil. So L is phi by I, or in general it is written as N phi by I. Flux, we know flux is proportional to I. The field which is induced or which is produced when a current is flowing through the coil depends upon the value of current. Flux is proportional to I, or I can write flux is L into I, where L is a constant which is known as self-inductance of coil. Now let us define the self-inductance. Self-inductance can be defined in different ways. So one way is, this self-inductance is also known as coefficient of self-induction. Next we will write the definition for self-inductance. Self-inductance or coefficient of self-induction. And it is denoted by L. One way to define it as, it is defined as the Weber turns per ampere in the coil. It is defined as the Weber turns per ampere. What does it mean? Now here in this equation we got phi is Li, or from this we can write L as phi by I. L is phi by I. Now if there are n number of turns in the coil, then the flux linking the coil will be written as n into phi. N into phi. Phi by I we have from the previous equation, L is phi by I. But if there are n number of turns in the coil, the total flux linking the coil can be written as n into phi divided by I. L is n phi by I. So this n phi is known as Weber turns. Weber, because flux is measured in Weber and n is number of turns. So Weber turns. What is Weber turns? Weber turns means the flux linkages of the coil, total flux linking the coil. And is given by Weber turns as number of turns multiplied by flux. Flux in Webers multiplied by number of turns with which the flux is linked. Number of turns with which the flux is linked. Therefore, L is N phi by I. Now, suppose if you have a solenoid with n number of turns, and if a current I is flowing, and if the flux produced is 5 webers, so N is the number of turns in the solenoid, I is the current through the solenoid, and if this current produces a flux phi, then the Weber turns is given by N phi, or L is given by the self-inductance. In this case, Weber turns is as N phi, and Weber turns per ampere. As N phi by I. Therefore, by definition, self-inductance L as N phi by I. We'll remember this equation because this we need for some problems. L as N phi by I. Now, what is the unit of inductance? The unit of inductance is Henry. I'll tell you how to define this Henry. Now, this is one equation for self-inductance. Now, we can have other equations also to calculate L. Now, in terms of self-inductance, the induced EMF is given by the equation E is minus L into di by dt. So, self-induced EMF in a coil is given by self-induced EMF in a coil of inductance L as coil of inductance L as E is minus L into di by dt. How do we get this? Because we know, I'll just show you the method here. We know E is minus d phi by dt. Now, phi is, we know also phi is Li, because L is phi by I. We don't take number of turns here. We'll just assume it as only one turn in a coil. So, phi is Li we get. And now substitute this. E is minus d by dt into L into I, and L is a constant, we can take it out. Therefore, E we will get minus L into di by dt. This is how we get this equation, because by Faraday's law we have E is minus d phi by dt, and by definition phi is L into I. Substitute that, we'll get E is minus L into di by dt, and you know the meaning of minus sign. It indicates that the induced EMF opposes the cause producing it. Negative sign indicates the opposing nature of induced EMF. L into di by dt. We need to remember this equation also. So, for induced EMF, now onwards we have two formulae. One is based on the flux. E is minus d phi by dt or minus N into d phi by dt. Phi is Li. E is minus d by dt of Li minus L into di by dt. Now okay, so if you want a number of turns in a coil, then also you can substitute that and you will definitely get the same equation, because here what happens is, I'll just show you that also. You have E is, if there are n number of turns, E is minus n into d phi by dt. And what is flux we have? We have L as n phi by I, or from this we have flux will be Li by n. Now you substitute that, n will get cancelled, minus n into d by dt of phi, that is Li by n, and n being the constant, n divided by n, it will get cancelled, minus n into L by n into di by dt. Therefore induced EMF is equal to minus L into di by dt. We need to remember only this equation. The self-induced EMF is given by minus L into di by dt. E is minus L into di by dt. The negative sign indicates the opposing nature of induced EMF. Indicates the opposing nature of induced EMF. Rest will continue in the coming session.